So again, the question is, of these 4 points, P, Q, R, and S, which one of them is closest to the line y equals negative 2x? So what did you try?
Plotting the points and deciphering from vision.
Great. So you plotted the points, as I did up here, and then kind of visually we can look and see which one of these is the closest? P. All right, so let's all agree upon that for the meantime. But what's the mathematical nature? What sort of techniques, what strategies did you use to try and unpack a thought process behind that that's more than visual? Greg?
We did the perpendicular lines from P, Q, R, and S to the line.
Okay, so you took and you drew lines like this, right, that pass through the point P and which are, you said perpendicular?
Yes.
Okay, so I heard the perpendicular story from a few different teams. Enough times to make me believe that there's probably something to that that we're going to want to explore if we can. Let's see. I think that's that one, and then here's this one. All right, so you drew these lines which were perpendicular. What did you then do with these lines?
We found, basically we used the MX, or we solved for where the B was, where the y-intercept was on
Okay,
those lines.
so for example, on this line, you found that the y-intercept is at, in this example looks like the y-intercept is 7.
And then we found where the two lines intersect.
Okay, so you would have found an equation for this line, which was probably something like y equals 1/2 x plus 7. And then we have the original line, y equals negative 2x. And then using those two, you could find the point of intersection by doing what?
Minus 2x equals 1/2 x plus 7.
Right, insisting that the y values be the same at that point on the two lines. And then using that observation to solve for x. So if we add 1/2 x to both sides, and then divide by 7.
3.
Oh, no, you're right. No, I screwed up. Yeah, no, so subtract, so I just need a negative sign here. Equals 7. And then we have to multiply by negative 2/5. Ugh. So x is negative 14 over 5. And if x is negative 14 over 5, then y is positive 28 over 5. And so that gives me the coordinates of this point. And then what do I have to do with that?
Take your x and y values and plug it into the distance formula.
Yeah, so we then have to go into the distance formula and figure out how to tell the difference, let's call this point P prime, the distance between P and P prime, using what is essentially the Pythagorean theorem, right? Because what we would be doing is finding the hypotenuse on this little teeny right triangle here in the middle, one of whose legs is the difference in x coordinates between these 2 points, and the difference between negative 14/5 and negative 2. Negative 14/5 minus negative 2, that's 4/5. So this little side, such a teeny diagram, 4/5. And so the distance is going to be the square, negative 4, depending on which way you measure it, yeah. So the distance would be the square root of negative 4/5 squared, plus, and then we measure the difference in the y coordinates, 28/5 compared to 6 is 2/5. So again, depending on how you reckon with positives and negatives, we'll call that 2/5. 2/5 squared. And so you'd go in here, you'd do this computation, we'd get 16 plus 4 is 20 over 25, reduce that down. What is that? The square root of 4/5. That's 2 square root of 5 over 5. And so you get the distance between P and P prime. But then what do? You do that again. You do it for Q, you do it for R, you do it for S. You do all that work, and then you pick the smallest of the distances. Great. Okay, that is certainly one valid approach to the solution of this problem. But what I want to call out is a couple of things. First of all, perpendicular. I saw that on, I think, everybody's papers. Why? What does perpendicular have to do with this whole thing? Okay, so there's something that causes the shortest distance between the point and the line to occur at a place which is perpendicular to that original line. So one of the big themes that we're going to continue to return to this semester is perpendicular, because what we consider to be perpendicular is not necessarily the same thing from problem to problem. Here, we're treating this like a problem in Euclidean geometry. Draw the line which makes a 90-degree angle with this other line, which we can do according to Euclidean geometry. Right? So we know what perpendicular is because we know how to spot it visually. But there's going to be a lot of power this semester in taking the idea of perpendicularity and pushing the boundaries of it. Figuring out how we can define angle measurement in different ways. If we define angle measurement in different ways, we define perpendicularity in different ways. And if perpendicularity tells us the shortest distance, then defining perpendicular differently will let us find shortest distances in different contexts as well. So perpendicularity is one major theme of applied mathematics. It also goes by a different name when we push the boundaries, called orthogonality, orthogonal. You'll see that word appears on our syllabus several times. This is the reason why. It's going to help us do problems like these. What else? What were some of the other mathematical kernels that you pulled out of this? Okay, so we had equation of a line, which actually helped quite a bit in this problem, but on the back side of the page, probably the techniques that you used on the front side didn't work so well anymore, right? We can't, it's not as easy to find an equation of a line which passes through, I don't know, Q, and which is perpendicular to this parabola. There are a lot more sort of problems with that. We can do it, but it's just a more complicated thing to do. Let me also submit that even just the very notion of distance is something that you, again, had to take for granted. If we're finding the shortest distance based on where something is perpendicular, what that does is it creates a relationship between perpendicularity and distance, or between angle measure and distance, that if we define one of them in one way, it defines the other one in a corresponding way. So Euclidean geometry is based on measuring angles in a Euclidean fashion and measuring distances in a Euclidean fashion, using the Pythagorean theorem to compute distances, with the distance formula, as many of you did, right? But if we define distances differently, that's going to define the answer to this problem differently as well. So in applied mathematics, those are the concepts that we want to push on. We want to take these familiar visual notions of geometry, linear algebra, and analysis, like measuring angles, measuring distances, and figure out how, once we understand what makes a distance, and we understand what makes an angle, we start to see them in other places that aren't just Euclidean geometry, but which might have the power to tell us what is the closest face to this other face that I just took a picture of. That's facial recognition. Or better yet, what is the closest musical pitch to this awful off-key note that Justin Bieber just sang, for example? Yes, that's another example of finding something. If we can figure out in what sense we can define distance and angle to make that happen, we can use those same techniques to approximate other things. And so the theme of applied math, just to wrap this up, is that we have something which we know. We have a space full of known objects. These might be the faces of our Facebook friends that we know, for example. And then we have something which is unknown, which is not a part of that set. And the question is, which element of the known set comes the closest to the unknown? And again, playing with the word closest, we're going to find ourselves in a lot of different contexts as we go through the semester.